I've been doing this for 35 years. I'm still fascinated by actually comes to listen to talk.
Jeff wouldn't. I don't think Jeff would have come in if it was anybody but you.
I'll take that as a
I
compliment.
think he would have just stayed and watched it.
I told them I was gonna stay home and watch and just watch.
Oh my God, you're not.
Oh, I am. Willie Dubs tees off in 20 minutes, 13 minutes.
What'd you say?
Willie Dubs.
Oh. Excuse me, go. Willie Dubs.
Rick Smith, double loading the first and 18th hole. Oh, I know.
Made 8 birdies. I'll sit over here so you guys are distracted by myself.
You see Jeff get worked up during class. We already know, you
No,
know.
I'll keep my emotions.
Will you really? Incorrect. Last time we were about to start the matrix exam and you threw your hat. So what? I'm so mad at this.
Don't worry, Tiger doesn't tee off.
We're not coming on.
She didn't. Yeah, and she was like, oh, I don't think you can focus with that. That's accurate.
During the exam.
Yes.
Oh, there we go. Okay, everybody. Let me, as tradition, say, and actually, until noon today, I'm caught up on the homework. So we'll see how it goes after that. So here's the next homework due next Friday. Number one, so this is kind of tying up some of the business we were talking about separability and finite fields and stuff. So let K be a field of characteristic P, strictly greater than 0, prime characteristic. Show if the degree of F over K is N and P does not divide N, then N is separable over K. And number B, I think we had a result like this in class, and this is kind of a generalization of it. If U and F is algebraic over K, then U is separable over K if and only if K adjoined with U is equal to K adjoined with U to the P to the N for every N greater than. So that's kind of a cool thing. Number two, this is kind of a fun one. Suppose K is a finite field, any finite field, and let F be algebraic closure of K, right? So you might think of like ZP. Okay, so take every polynomial over ZP, throw in all the roots, and see what that looks like. Number one, show the Galois group of F over K is a field. Right? And basically, I'll give you a hint on that one. All you have to do is show that given any X and F and any two automorphisms, sigma 1 and sigma 2, then sigma 1, sigma 2 of X is sigma 2, sigma 1 of X, right? And X, of course, is contained in a finite field if it's algebraic, so that might help. And this one's kind of interesting too. Show that if you look at the automorphism group of F over K, you have the identity of automorphism, of course. If you have a non-identity element, it's of infinite order, which is really cool. Notice that the separate elements, any extension of finite fields is a cyclic Galois group, and that'll help. But if you have an automorphism of the entire algebraic closure, every element actually has infinite order. Number three, let F be an extension of K, and let U and V be elements of F such that U is separable and V is totally inseparable over K. So they're kind of opposite of each other. One's separable, one's totally inseparable. Show that K of U plus V is the same thing as K UV. Notice one containment is fairly obvious. The other one, you'll need some of this other stuff. And also show that K UV is the same thing as K of U times V if both U and V are non-zero. You don't need that condition on the first one, but okay. Any questions on that? All righty. So the last time I gave you some stuff that basically it deals with quartic polynomials over a field of characteristic not 2 we looked at the special, resolvent cubic and showed basically how you can tell what the Galois group is. There are 5 transient subgroups of S4, and we basically dug all this out. And the last thing I gave you was this theorem. Suppose F is monic of degree n. And P of positive prime. And see. Suppose that Fx, and by this I mean reduction mod P, by the way, you don't really need f of x to be monic, but for what you need is this prime to not divide the leading term, right? Because notice if it's not monic, and let's say that an is the leading coefficient, if p divides that, then when you reduce this mod n, it'll drop at least 1 degree, right? So suppose that the reduction mod p has distinct roots in its splitting field. Roots. Then if over CP, the reduction is of course polynomial over CP. Then if f of x factors as irreducible factorization, F bar equals G1 bar, G2 bar, GK bar, I guess it was, over ZP X. So take this reduction and factor it mod P. See how low you can go, factor it into irreducibles. And suppose that the degree, I'm going to let the degree of GI be MI, that of course I'm assuming is at least 1. Then there exists an element of the Galois group of F over Q of the form C1, C2, K with each CI and SN, a cycle. And the proof of this is not terribly difficult, but it's really cool. This is actually a very cool thing because what it does is it takes this monic polynomial up here of degree n in Zx, and it translates it to mod p, where I mean you've only got finite many ways to factor it. So this is you can algorithmically figure out what the factorization is down here. And once you've done that, this tells you that just read the degrees here, then you have to have a cycle decomposition in your Galois group of original F that looks like this. Let me give you an example of a rather amusing application of this that I have one time. We are going, here is 8511. Using Galois theory to prove don't take a makeup. I will use Galois theory to prove the statement. So this goes back to, I'm going to actually do a calculus problem. Go see the links I go to in the class just to amuse myself and others. Gave a calculus test one year. And one of the problems on it was this. I had the so the problem went a line, such that region first quadrant is split into two equal areas of region. Right, so you take what's bounded by the x-axis in this parabola. I want to adjust the slope here so that I'm actually splitting into two pieces, right? Everybody cool? Now, I think I need to work through this problem to make you probably appreciate this. This is also kind of an apocryphal story about teaching too. The problem itself, when I assign this problem, is a little bit obnoxious to actually find the exact value of m. So basically, if they did everything right, couldn't quite finish it off, they're going to get like at least 80% credit, right? Or 80 or 90 if they set it up right. Because to actually find the value is not impossible, but it's obnoxious. But this was kind of one of the centerpiece problems on my exam. So let's do the problem. The area, well, the first thing I might want to do is find the intersection point. And the intersection point, of course, one of them shows up to 0, right? Which one would expect. 1 minus m over a. So this intersection point right here is 1 minus m over a. And then the easy way to do this is m times 1 minus m over a. Agree? And the area, the total area, is the integral from 0 to 1. Let's see, of course. So this is 1/3 ax cubed minus 1/4 ax squared. So that's going to be 1/12 a. Okay, so far. So that's the total area. So basically what I need is I need for this to be right.
I think it's just supposed to be AX and out of the integral. I think you did the integration right.
Oh, this is supposed to be the fourth, there we go. Everybody okay with that? Yeah, that's what we want. Did I address your concern?
Shouldn't it just be AX squared minus AX?
Oh, yeah, of course, I thought that answer was wrong. So I've already messed that up, haven't I? Yes, thank you very much.
Yeah, that's why I think you've done the integral right, you should get it wrong thing.
I was like, you don't have much.
There we go. This is-
It's been a while.
This is
since
what, because I actually worked this problem the other day to make sure that I still
That was my
could.
assumption.
There we go, better, 1/6 thing, right? So this is actually, so what you need is for this to be 1/12. That's what I'm familiar with. So notice it's easier to get this piece than the other one, right? Because if you integrate, nobody wants to integrate this with respect to y, because you got awful, right? And you don't want to integrate the bottom half with respect to x, because that's going to require you to do two integrals, because your top is the line and then the parabola. So it should be this minus this. So the easiest way to do this is you want half of this to be integral from 0 to 1 minus m over a, which is the x coordinate of the intersection point of the top, which is the parabola. I'll get it right this time, minus the bottom, which is the line. Everybody okay? So this is equal to a minus m x minus ax squared from 0 to 1 minus m over a. And so I get 1/2 a minus m x squared minus 1/3 ax cubed. Like that. Now, one of the things I can do is I can pull an x squared out of this. And so this is actually 1 minus m over a squared. That's my x squared I pulled out. I get 1/2 a minus m. And then I get minus 1/3 a times 1 minus m over a. Everybody okay so far? So notice I can put this a back in here, and then I've got this factor of a minus m here. This is 1/2 a minus m minus 1/3 a minus m. And so this is 1 minus m over a squared. That's going to be 1/6 a minus m. So now I'm going to make this all an a minus m. 1/6. What did I do? I put 2 a's here, so right. And at the end of the day, this is supposed to be 1/6. I'm sorry, 1/12. And so, really the calculus is done about right here, right? And this is where it's a little bit kind of yucky. Because what this is this is 1/6 a minus m cubed equals 1/12 a cubed. Right. And so kind of to finish it off here. I get, what do I get? A minus m cubed over a cubed 1/2. So I get, take the cube root of both sides, I get 1 minus m over a is 1 over the cube root of 2. And so solving this for a, I can get that's a fun little calculus problem. I like that. Now, unless you completely think I've lost my mind. So the calculus is not too bad. I did kind of a substitution here, noticing that these a minus m and this 1 minus m over a were kind of related. A lot of students don't see that. They start multiplying this out, and it's, you know, that's why they can't solve it. They get this horrible cubic, and it's hard to see what the roots are. And that's why, you know, up to here, they probably get between 80 and 90% credit, right? At least on the exam. Well, so there's the problem. Now, when you teach a large lecture calculus class, you always got slackers. And I went through 2 makeup tests on it. I had some people that said, oh, you know, I couldn't. Anyway, so I was like, yeah, sure, I'll give you makeup. So they came back and made makeup. This one guy, he kept missing the makeups, and I kept making up more makeups, and then he wouldn't show up, make me a little bit angry. And so I had this skeleton written up for this guy for the makeup exam, and he shows up. And I was actually surprised he showed up because he had ditched on me 3 times. And I was like, okay, go sit out there. It'll take me 10 minutes. Because I was like, that's the problem I had replaced. I was not going to give them the same problem. It's not fair. I already had the thing posted online. So I had to come up with a new centerpiece problem. And it can't be any easier. That's not fair, is it? So I was like, what do I do with this problem? So I was like, I know. Rotate this around the x-axis and find the slope that cuts it into 2 equal volumes, right? Why not? Same sort of thing, right? So instead of just the area, we're spinning around to get the volume, right? So I changed it and gave it to the kid, and I sat there doing my work, and then I got bored, and I sat down and I said, well, I'll solve this problem myself. And so I did. And after an enormous amount of reduction. I mean, of course, this guy, the same as the other, I would have given most of the credit just to get the calculus right and set it up. But actually to find the value of the slope, which here involved obviously a cubic, right? We had to extract the cube root. I went through, and I'm telling you, I'm not putting you through this. I put myself through it, and it was unpleasant. I reduced this to having to solve this equation. 8x to the 5 minus 10x4. And believe me, there was a lot of stuff that went into reducing it down this far. And of course, at this point, I'm like, uh-oh. And I thought, gee, I wonder if I can even solve it by radicals, right? So let's apply the theorem. I won't put you through a lot of stuff. Notice this is not monic. And I like this example because it illustrates why you wanted it to be monic, but you can dodge that bullet. Because what happens if you reduce this mod 2, you get the polynomial 1, right? But as long as you're away from 2, right, which is the only factor of 8, you're good to go. I reduced this finally mod 11 And I got 8x5 minus 10x4 plus 1. When you factor this model 11, I got the following. Well, actually, I did pull the 8 out so I could make it mnemonic and make it easier. And of course, 8 mod 11 is just some other unit. X squared plus 9x plus 6 times x cubed plus 9x squared plus x. I think that's what I got. Yeah. That's what I got from mod 11. If you multiply it back, you can, I did check myself the other day. If you multiply this back, you will get exactly this polynomial mod 11. And I claim that these are irreducible, and I won't make you check. I actually did recheck this myself. Basically, what you have here is a quadratic and a cubic, right? And so it's easy to test for irreducibility there. All they have to do is not have a root, and they're irreducible. And I ran through the root, I ran through all the numbers, mod 11, and none of these have roots. So this is an irreducible element, or I'm sorry, 2 factors are irreducible, mod 11. And so here's the final question. Galois group of this original polynomial, 8x5 minus 1. Well, in Galois group of F, we have an element of the form A, B, C, D. We have a 2 cycle times a 3 cycle. Right? So, what does that tell us? We have the 2 cycle and 3 cycle. Well, that's fine. Okay. If you have in, well, it doesn't matter in SN, as long as n is bigger than or equal to 5. If you have a 2 cycle times a 3 cycle, they're disjoint here. That's why I use the different letters. What's the order of that element? It's of order 6. This group has order 5. This has order 10. This has order 20, 60, and 120. But I can tell you exactly which one it is. Do you know which one it is? So I eliminated 3 of them by noticing it's got an element of order 6. But this is also odd, right? Because this is even times another transposition is odd, so it can't be a 5. So I gave that poor slob a polynomial equation to solve that had Galois group that's 5. So it's sort of hopeless for the fellow.
So he didn't get it.
Well,
Pretty impressive.
I put a lot of effort into that project. I got the exam back, and he didn't even try it. He didn't put pencil and paper on that problem. So, oh well. But it made for a great story. So I guess it was worth my
I was
time.
really wondering how we were getting back throughout that whole calculus problem,
Yeah, well, there was a method to madness.
or how were we getting to don't take makeup exams with Jim.
Well, there you go. See, now I can really say that I'm doing applied math. Any questions on that?
Your little calculus error just reminded me, yesterday David was gaslighting me during his presentation at the seminar because he had us do the derivative of a polynomial that was factored and just like out using the product rule and then just using the power rule. And I kept doing it and getting different answers when I used the product rule and the power rule. And I was like, I don't know how to take the derivative of polynomials anymore. But he factored it wrong. So they were two different polynomials.
Oh, there you go.
And I was like, oh,
That'll do it. Here's another, I like this theorem. I mean, this is actually, plus the previous one. Theorem, this is kind of an interesting one, and I'll give you a short proof of this one actually, because actually the proof is sort of cute. Let P, this one's certainly a little bit more specialized than the previous one. Let P and Z be positive prime. And suppose that f of x is irreducible of degree P. If contains, if f of x has precisely two non-real complex conjugate roots, then Galois group F more symmetric, full symmetric SP. Okay. So in other words, so if you have f of x equals a cubed x squared cx, well, let me just take, I'll just make it mod a so I don't have to worry about whether it's correction. If it looks like right. If it looks like that, we got one that. Right, has to be, because this root has, according to this theory, exactly two real complex conjugate roots. Or, for example, some a quick illustration, if f is equal to x5 plus ax4 plus b squared dx. And it looks like this. Is that right? 1, 2. Then, yeah. We got one root of n. The reason this works is Galois root yes, is a transitive subgroup And must contain P cycle. Because remember, it has to be a transitive subgroup of SN, and it has to contain an element border in. And so in SP, of course, the only elements of order P are the P cycles. So without loss of generality, you have 1, 2, 3, 2. And since only 2 roots are non-real, say corresponding one and 2, then 1 and 2 is in Galois. Because complex conjugation, since there are complex roots, complex conjugation is going to be a non-trivial automorphism. And since there's only 2 non-real roots, complex conjugation swaps those 2 roots and it leaves the rest of them alone, right? So you have a P cycle and you have a transposition. And one of the results we had in 8510 back there somewhere is every element of or SP, or actually SN, is generated by an N cycle and a transposition, right? So once you have this P cycle and you have a transposition, it doesn't matter which one you have, then you can generate the entire group. Okay. Any questions on that? Okay, so the last thing I want to do in this section is rather, I like to call this my bag of tricks section for doing this. I'm going to give you, so in long last, I'm going to give you something that will always work. It will universally work. And you'll probably never want to use it, right? But it's like one of those desert island things, like, you know, oh, well, I guess I could if I needed to, right? This little trick will always work to get the Galois group over Q. This is an algorithm that's in an old book by Eugene Dickson, an old number theory book kind of thing. So if you want to reference this, I can give that to you too. I've got the book somewhere actually. Let me sketch how to do this. Suppose you take your favorite polynomial, irreducible, QX. We describe how to find Galois group. And this goes in a number of steps. So yeah, this is irreducible, so it's separable. So let Z1, Z2, Zn be roots of and so here I guess I'm assuming that F has degree N, because notice F of X is irreducible, and since we're characteristic 0, it's a separable polynomial. So these will be its N roots, so the degree is N, and these Z1 up to Zn will all be distinct. Now, introduce the indeterminates. So basically, here's the way this construction works. you take the n roots of the polynomial, and you don't know what they are, but this is an abstract construction, so you can always kind of figure it out. You can use properties of the polynomial to figure it. Even though you can't find the roots, you can get enough to get this out of here. So with x1 up to xn, so basically you introduce a new polynomial variable for every one of these roots, right? Now, what I'm going to do is, of course, Galois group of F has to be a transitive subgroup of Sn. So I'm going to use Sn to kind of dig it out. So if I give you a sigma in Sn, I'm going to find this thing that I'm going to call E sigma. And it is going to be C sigma 1 x1 plus C sigma 2 x2 plus Z sigma n. Right. Notice that I can do this for any permutation, and notice what this does is see what sigma in Sn takes the element 1 somewhere, right? Maybe it takes 1 to 2 or something. So this would be then Z2 x1. So this is basically kind of shifting, permuting all these things around. There should be n factorial of these things, and let G of x equal product of x minus is sigma, a sigma in Sn. Now, you're already seeing that perhaps this is a little bit computationally inaccessible, right? Because if we go back to my 5th degree polynomial that I just had, then this polynomial here, and notice this is a polynomial, this is a new variable x, right? And these things right here consist of these other polynomial variables kind of interspersed with the roots, and the degree in the variable x will be n factorial. So even for my polynomial, you're looking at a polynomial that's degree 120 in the variable x, right? Now, each coefficient of xi of g so you read through this, and this is of course a polynomial in x, but you've also got the coefficients of that polynomial are in the variables xi, and each coefficient, let's call it ci of xi, is actually in the and actually, I would encourage you to do this for something like, do this with a quadratic polynomial, right? Even though it's Galois, you know what you should get. This is actually symmetric in the roots. So because it's symmetric in the roots, that means that it's invariant under the Galois group. So each ci, that is the coefficient of xi, is, let's see. Actually, I mean the coefficient of x there. So each ci is a rational function. In the variables x1, x2. Because the, is a polynomial with rational coefficients. Polynomial. Because of the fact that the coefficients are symmetric in the roots, that means that the roots are in the base field, which in this case is Q. So what you get is this big polynomial in X, and the coefficients of this are all rational functions, I'm sorry, polynomials with rational coefficients, and they're polynomials in variable x1 up to xn. So once you multiplied this out and got what this big giant g of x is, then g of x over the ring. So the coefficients come from these polynomials over Q and these variables. Factor this polynomial g of x in this ring here. So it'll have an irreducible factor of this. Let G0 of x be the irreducible factor of G of x, such that EI is a root, where I is the identity permutation. That is to say, EI, let's go back, this is just Z1, X1, plus Z2, X2. So notice that, of course, in this product here, EI is one of these products, right? And of course, it's linear. It comes from a linear factor here, but of course, these things are not rational functions because they involve these roots over here. So you put this big mess together. One and only one of the irreducible factors will have that EI as a root. It'll appear in one of the clumps, one of the irreducible factorizations. The Galois, so here's the end game here. The Galois group of F will consist of permutations that fix this. Permutations of x1, x2 that fix. So in other words, G naught x, you pull out this irreducible factor, it's going to be a polynomial with coefficients in these variables here. Look at all permutations of those variables that fix G naught, right? Of course, permuting these variables basically corresponds to a permutation of n things. So in the end, collect all those that fix that, and that'll be your Galois. So this is not very easy to implement, but it can do. I challenge you to do this with a quadratic, right? And if you're really feeling, froggy, then, do it with a cubic. So, but it gets out of hand pretty quick, but it always works.
Yeah, that's what I did on the home of the 3-6 polynomial. I did with my 720-degree polynomial.
Yeah, that's not bad. Okay, any questions? Any questions? Well, the math club today, Marvin Jones is actually going to talk about this visual cryptography stuff. And I know some of you are interested in this kind of thing. It should be kind of a fun talk, so I encourage you to be there. Other than that, y'all have a good weekend, and I will see you on